We're going to take pipelining to the next level. We're going to take it to super pipelining. We're going to look at parallel execution of instructions. So the assumption here is that we're building extra hardware in order to do more than one instruction per clock cycle. In other words, our CPI is going to go less than 1 because our IPC, the inverse of it, is going to go greater than 1. It's going to be more than 1 instruction per cycle. So when you take the inverse of that, CPI is going to be less than 1. Okay, we all know that dropping CPI is going to drop the time, right? CPI is one of the key factors in the time equation. So what I'm about to show you for the next couple hours are advanced processor architectures which will help us to get a parallel execution. Now, parallel execution of instructions means that in a stream of instructions, I can pull out them and say, you go to that processor, you go to that processor. In other words, it assumes that they are parallelizable. Parallelizable. That's the Varsium, right? Yeah, it's almost the same, isn't it? And so, it means that we have to have something called instruction-level parallelism. Instruction-level parallelism. Now, there's other levels of parallelism. There's thread parallelism, there's process-level parallelism, and there's program-level parallelism. Okay, so this is done at the instruction level. This is called fine-grain parallelism. Literally, it would be picking out the brown grains of sand from the black grains of sand and saying, you be in this pile and you be in this pile. So it depends on the way the program is written, depends on a number of factors. But there is instruction-level parallelism in most programs, and we can extract it and run it in parallel processors. As you know, the number of cores is rapidly rising. So any instruction-level parallelism that we can find in software in advance or in hardware dynamically real-time will help us. So we'll talk about static parallelizing. That's done by the compiler at the time that the code is looked at. And we'll talk about dynamic parallelization, which is done real-time by extra hardware. Just like the extra hardware that does branch prediction, just like the extra hardware that does a number of things that we talked about in the last section in order to find and extract the parallelism. If there is no parallelism, then it doesn't help us to have extra hardware. In order to get performance, we have to have both the parallelism in the code and the hardware to support it so that it can run in faster than CPI equals 1. Do we understand ourselves? So we need two things. We need to have it in the code, and we need to extract it and run it in the hardware. The hardware isn't there, it doesn't matter how much parallelism is in the code. If the parallelism in the code is great but the hardware is not there, we don't gain anything. It's got to be both and, not either or. Okay? All right, so let's take this into the lecture and see where we go. Okay, we've talked about structural hazards, data hazards, and control hazards. All of these exist whenever you go to a pipelined architecture. We talked about what to do with these. Design the pipeline, if possible, to eliminate structural hazards. Short pipelines with late write work a lot better than longer pipelines. Read before write or write after read uses data forwarding inside the pipeline. And for the cases where the forwarding won't solve, we have to detect the hazard and we have to stall. For control hazards, you can kind of tell. Easy to solve, not too hard to solve, hard to solve. Just look at the quantity on the slide. We spent a lot of time talking about how to handle the control hazards that come from conditional branches. I won't go over all that again, but we looked at a number of options last week. If you weren't here last week, I'm really sorry. You missed some very important, very deep, and very powerful concepts. So please, please study the book. Please look at the lectures. Please watch the video even again in order to get what you missed. Okay, now, to get even more performance, we're going to have to move from one pipeline to more than one pipeline. Okay? We're going to increase the depth of the pipeline to increase the clock rate, or we're going to add parallel pipelines. Now, super pipelining just makes a pipeline deeper and chops the amount of work done in each section smaller and smaller, therefore a faster and faster clock cycle. I think everybody can see that. If I have this much work to do and I chop it into 3 pieces, I have a 3-stage pipe with a clock this long. If I chop it into 30 pieces, they're all very short. The clock can be very fast, but I've got a deeper pipeline. All the hazards become worse when the pipeline is deeper. The data hazards coming from data dependencies, the control hazards, even the pipeline static hazards or structural hazards become worse. All right, that's one way to go. Okay, we talked about that briefly. Now, here's what I'd really like us to look at, and that is multiple issue. Issuing into parallel pipelines more than one instruction at a time. Okay? Fetching and executing more than one instruction at a time is going to require expanding every pipeline stage to handle multiple instructions, or just duplicating the pipeline, you might say. The instruction execution rate, the CPI, is now going to go less than 1. So instead, we're going to use IPC and try to get that greater than 1. An IPC of 4 means a CPI of 0.25. An IPC of 8, if you had 8 pipes, then it means a CPI of 0.125. That's the goal here. And so a 6 gigahertz 4-way, got it, 4-way, there's 4 instructions at once, multiple issue processor could therefore execute at a peak rate of 24 billion instructions per second, because every clock cycle moves an instruction down to the next stage in the pipeline, right? So 6 gigahertz means I do 6 billion instructions per second, but now I've got 4 pipelines, or I'm doing 4 instructions, moving them forward every clock cycle, so it's 4 times that rate, or 24 billion instructions per second. With a best case CPI, of 4 instructions per cycle finishing, or CPI of 0.25. So these are my best case. That's if I can keep all 4 of those pipelines full all the time. Can I? Depends on instruction level parallelism. If I have it, yes. If I don't have it, no. If I have it on average, then sometimes it will, and sometimes I won't be able to find 4 that can be parallelized. And so I'll feed this pipe, and I'll say to these 2 other pipes, sorry, you have to go hungry. There's no meal for you. I haven't got instructions to give you which are independent from those that I can give you. Okay? If the data path has a 5-stage pipeline, how many instructions are actually active in the pipeline at any one time for this machine? 5-stage pipeline runs at 6 gigahertz. It's a 4-way multiple issue. How many instructions are actually in the pipeline at any one instant of time? 20. How'd you get that? Because there's, in a single pipeline, there would be 5, and now I've got 4 of them. So there's 20 instructions that are in this system, and you can imagine they're going to probably have some dependencies. There'll probably be some hazards. There'll probably be some conditional branches. There'll probably be some data that's, gets a little tricky, doesn't it? It was already interesting with one pipeline. Now it's going to get very interesting. Imagine pointers pointing backwards and forwards from all the dependencies. Okay, so our goal is going to be able to sort that out very well and get the maximum use out of it. If you have 20 instructions processing in that example, Nemut Lusana, you've done a great job in your parallelizing, if you have. Obviously, it'll be hard to get that. That's why it says best case CPI, when you don't have to have any stalls. Okay. All right, let's look at types of parallelism. We talked about instruction level parallelism of a program. That's a measure of the average number of instructions that a processor might be able to execute at the same time. IPC. ILP, instruction level parallelism. Very, very common. Okay, mostly it's determined by the true data dependencies. You know, is this one needed for that one? And procedural dependencies like the jumps, and especially the conditional branches, in relation to the other instructions. But there's another kind that I'd like to talk about here, and that's called data level parallelism. And data level parallelism, if you just quickly look here, do from I is 1 to 100 the following thing. Fetch the element, add 1 to it, put it back where it came from. So you can see that working on element 27 is a completely independent activity from working on element 58. Fetch them, add 1 to them, stick them back. I don't have to wait for one on the other, so you can see that that has data level parallelism of 100 for that loop. Data level parallelism. Got it? Get from memory, add in, increment in the processor, stick it back in memory. There's 3 things that have to be done in a loop. Total 300 instructions. In a single processor, you're going to run a loop 100 times. It's going to have 3 things in it. If you parallelize here, we might be able to do it in 100 processors. Boom, 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 and we're done. Right? Now, obviously, there's issues about memory access to read it and memory access to write it. But if I had 100 ALUs, I could clearly do this operation with parallelicity or parallel degree 100. Okay, now, these are in the code. Data that's parallelizable in the code, instructions that are parallelizable in the code. Now the question is, what's the machine got to support that parallelism? This won't give you any speed up at all if you just have a single processor. And if you have 2 processors, it'll give you a speed up of 2, even though you could have a speed up of 100. And that's because the machine parallelism is limiting the ability to do the data parallel work. A machine parallelism is the measure of the ability of a processor to actually take advantage of the instruction level parallelism or the data level parallelism in the program. It's determined by the amount that you can do in parallel in the hardware. You've got to have the hardware in order to be able to do it. Okay, so to achieve high parallelism, you need both the code to have it and you need the machine to support it. That's the point I made earlier. That was the introduction. I'm saying it again because it's the key point in this section of slides. Now let's look at ways to issue multiple instructions, how to organize the hardware in order to issue multiple instructions at the same time. There's two basic approaches, and one is static and one is dynamic. They start with the key headers here. So you know right away, static means before we start to run, we figure it out, and dynamic means as we're running, we figure it out, real-time figure it out. The static one is therefore going to require compiler support, very heavy compiler support. The dynamic one is going to therefore require very heavy transistor support. Either you're doing in computing the algorithm in transistors or you're computing it in code on a general purpose processor. If you build it into the transistors, you can do it real-time dynamically in the hardware. If you don't build it in because you don't have the budget for the transistors or you think you can do it well enough offline, then you build it into the compiler. Okay? What are we doing? We're making, in this case, VLIW, very long instruction words, and you can imagine the compiler generates multiple things to do in one instruction. So they get really long. Do this on this data, do this on this data, and do this on this data. Fetch it all at once and launch it all at once. If you have the three pipelines and a very long instruction word, and if the compiler was able to find something to put there, find something to put there, and find something to put there, you're good to go. You're good to go. This is the approach taken by the Intel processors. They do this static packing, and obviously it depends on the compiler analyzing the code and saying, you can go here, you can go here, you can go here. So there's an organization required by the compiler to support this. By the way, it's a good time to give a commercial for our course. You'll have 5 technical electives that you can take in your curriculum, and I'm going to mention to you one of them right now. It's called Compiler Design. Okay, we offer this course. Ilyas Hoja is the professor for it. There's a lot of stuff that I've touched on in this course that should cause you to say, wow, I guess compilers are pretty interesting. They're pretty important for performance. They do some very challenging jobs, and they're more than just push the button, okay, now it's compiled. I mean, maybe that's how you want to live your life. Just push the Java compile button or push the C compile button. Yeah, maybe, but that's a really, really, really tiny DAR view for a computer engineer who's supposed to have a very wide view. Now, I've touched on compilers a little bit in this course. It's not a course in compiling, but you know how important they are because they keep coming up as it turns to performance. Here's one more place. VLIW cannot be done without compiler support. So I encourage you to think about in your 5 technical electives, maybe taking the compiler course. All right, so Intel's Itanium and Itanium 2 series for their 64-bit ISA called EPIC, explicit parallel instruction. Get it? It's explicit. Here's one, here's another one, here's another one. There's nothing hidden about it. There's this long word, and you can see there's 3 or 4 instructions packed into the word. It's explicit, so they call it EPIC. Okay, I think you also realize that EPIC is an English word that means, you know, wow, it's huge, it's great, it's wonderful, it's grand, it's famous. You know, the idea of epic and epic, they just picked an acronym to make it sound like it's really great. What they do is they make bundles of 128 bits, and they contain 3 instructions in the bundle, the long instruction word, which are 41 bits each. The instructions are 41 bits each. And then so the 3 times 41 gives us 123. And then they have a 5-bit template at the beginning that gives information about what the hardware is going to find in the rest of the 128 bits. Okay? And the template specifies which function unit each of the instructions needs. So the first one might need an integer function unit. The next one might need a floating point function unit. And the third one might need the control function unit, the branch and jump function unit. Okay? So the 5-bit template field just tells the hardware who you're going to find and where it should go when you execute it. Okay, it gives 5 functional units in the hardware, so we only have parallelizing of 3 in the software, but there are 5 different function units. There's an integer ALU, there's a floating point ALU, there's a branch unit to handle the control ones, there's a multimedia unit, and there's a memory unit, data memory unit. Obviously the fetch always comes from the instruction memory. So that one's going to be if you're going to go to memory for reading and writing. These are going to be if everything you need is already in the processor's registers. But we're splitting integer from floating point, we're splitting control from data, and we're splitting multimedia ones, which are little mini parallelizable bits for, graphic field or sound from normal data that we would execute here and here. Anyway, then in addition to that, this hardware also has extensive support for speculation and for predication. Now, speculation is predicting the future, and predication is putting conditions on the prediction of the future. We'll talk a little bit about both of these, but there's much more data in the chapter. So if you're interested in how Intel has gone for high-performance processors, check it out, okay, in the chapter. All right, now the alternative to doing it statically and putting all the intelligence in a compiler and trusting that the organization of the multiple mini instructions inside the big long instruction is going to be giving you the best performance. The alternative to that is dynamic multiple issue. So static multiple issue, go boys, go into my pipelines. Got 3 of them here in the Intel example. 5 of them, but only 3 can be pushed at the same time because only 3 come with an instruction word. Here, instead, we're going to be doing it in hardware. And the advantage of that is you're not saying in advance, I can only have 3. In hardware, if you have 5 pipes and you find that the instructions are all able to run in the 5 pipes, you can push them all into the 5 pipes. Okay? We're going to be able to fill all the hardware capacity that we have if we do it dynamically. We also get the advantage of seeing how the flow of the code is going. As you know, code has branch points. Loops have branch points, and so you can't know that in advance in the compiler when you'll go this way, when you'll go that way. But with the dynamic, you're actually seeing how the data, which is tested, and the results that are created cause the code to flow, and you can adjust a little bit more real time. So the decision about which instructions you're going to execute simultaneously, anywhere from 2 to 8 usually, because that's the degree of instruction level parallelism that can be found in reasonable code, is being made at runtime. So we've got anywhere between 2 to 8. We're looking at a group of the next instructions saying, hey, I can get 4 of you guys in parallel. Go, boys, go. Or, hey, I can get 6 of you in parallel. Go, girls, go. Or, oh, it's only 2. All you guys are connected together. So here you, 2 more. Depends on the degree of parallelism in the code. It's dynamically adjustable. Have any famous processors chosen this? IBM has. Intel has for the Pentium, MIPS has, AMD has for Barcelona. Yeah, it's used as well. Okay, now with multiple issue, there are some responsibilities for the data path that we didn't have when we had single issue. When you just had a single pipeline, life was simple. Simple, Natimex, simple, Hoja. We're just about to do a Kojimon project and we're scared to death. We don't know how we're going to manage a pipeline. Single cycle was hard for us. Natimex, it was simple. Well, compared to this, it was simple. When you had one pipeline, we didn't have to do the kind of things that we have to do here with multiple issue. Let's have a look at the things you have to do for multiple issue. You've got to be able to handle using the hardware and the extra transistors you're going to build in, plus any software help that you're going to get to fix the following problems, okay? The limitations of how many instructions are you going to be able to issue in a clock cycle. Those are called issue slots. In other words, you look at the code and you say, it's clock time, I've got to send somebody into the pipe. How many can I get and which ones, okay? So that's the question right there. That's got to be figured out one way or another. We talked about how the compiler would do it with that prefix field in the EPIC architecture. We haven't really talked about how you do it dynamically in a hardware architecture. Then you have to look at dependencies, okay? What things are linked to what else, other things? Remember the linkage of I change it here and I use it here was crucial to the whole business of trying to solve those hazards and forward around them and all that stuff. All our trouble in one pipeline came from that kind of thing. Now we're going to have a lot more of those, okay? Data hazards. And the limitations are going to be very severe in the VLIW processor due to the unusually low ILP. I mean, with VLIW, there's not going to be much you can parallelize between them because it's already been extracted and put into one instruction. So I don't expect the next one to be really independent from the last one because I've probably already taken the independence and pushed it into the fields. And the other issue that's big is procedural dependencies. This is the issue about control hazards. It's even more severe than this, and that says that's severe, even more severe. No, I'm sorry. We're saying more severe than in a a single pipeline. So now we're in multiple pipelines. It makes it worse. And we're going to use dynamic branch prediction. It's crucial. We couldn't imagine any of the other alternatives that I showed you last week. None of them will anywhere close to the challenges here. We've got to use dynamic branch prediction to help resolve those issues about where do I go next and what should I do now until I know the decision. And then we've got resource conflicts. We've got structural hazards as well. A superscalar or a VLIW processor has a much larger number of potential resource conflicts. And so the functional units may have to arbitrate. Even if you have 5 ALUs and 5 register files and, well, 5 register files. That sounds like trouble, doesn't it? Because now it'd have multiple copies with different values of T0 or R5. That right off the bat you can see that sharing things like buses and registers are going to be important. Yeah, you can duplicate ALUs. It's fine, you can duplicate things like multiplexers, but a bus is a bus. It's to get from A to B. If I make a different one to get from C to D, then C can't get to B, and A can't get to D. So in the end, I end up sharing, don't I? So buses are shared. Any storage is shared, like data memory or my register files. So I've got those kind of issues. And the functional units might have to arbitrate. Arbitrate means contend for or fight for access to the result buses or the register file write ports. If I'm going to write something, yeah, reading, we could put lots of parallel reads, but when I write, there has to be a SURA. And finally, resource conflicts can be eliminated by duplicating the resources, if you can, or by pipelining the resource. Right? So I've got some resource. Either I have to make 2 of them so it can be used twice at once, or I pipeline somehow so that the accesses are all very well organized. Big challenges, big challenges. Now, speculation. I mentioned that the EPIC uses speculation. Actually, a lot of these approaches use speculation. Speculation is used to allow execution of future instructions that may depend on the speculated instruction, right? So I'm assuming, for example, that this speculated instruction takes me that way, and I start to execute in the future. It seems like advanced knowledge, okay? So you speculate on the outcome, for example, of a conditional branch. We've already kind of talked about that a little bit, so that's called branch speculation. Or you could speculate that a store which precedes a load does not refer to the same address. And that would allow me then for the load to be scheduled before the store. Right? Can I do that in marker on the board? Store precedes a load. I got store word, load word. Now, in order to rearrange that, this would have to be independent from that, because the case that I certainly don't want to do is store X to address 27 and then read from 27 and put it in Y. Got it? If these are the same, then I can't change the order. But as soon as these become independent, doesn't matter now. Now this can be independent from that. I could move the load up before the store. Why would I want to move the load up before the store? And see why now? Why? Why? What do we call that? Load use. Causes a hazard, doesn't it? We have to stall and put in some tea drinking right here. What would happen if I did this? Well, we're great. No tea drinking. We can do useful work as long as this doesn't cause a problem with that. So the real issue is not, are these the same? The real issue is, are these the same? So you can speculate that they're different, right? If you speculate and you're right, you just keep rolling. If you speculate and you're wrong, what do? You speculate on a branch, you went the wrong way, oops. You speculate on the store and oops, what do you got to do? Roll back and go the other way. Roll back means cancel everything that started doing, including, and most importantly, any writes. Ooh, man, if you went down the wrong road and you wrote some things, then rolling back means unwriting them. Or maybe that would be too hard. Maybe don't really write them, just schedule them to be written. And then if we find out it is the right road, then they write. Okay, so they're scheduled, and we can go, erase it off the schedule. Because if you write something, unwriting it means keeping a record and then having to go back. And so it'd be better just to hold on the right. Anyway, you can see there's going to be some issues there. You're going to have mechanisms in hardware or software to check if your guess was correct and recover from a wrong guess if it was wrong. If the guess was wrong, you've got to go back and go the other way. So you need some recovery mechanisms there as well. Okay, now what you've got to also do is handle exceptions. Think about this. I go down this road, I've speculated, and it caused some exceptions. Okay, now tell me, should I actually do those exceptions? Well, wait a minute. Maybe the road I speculated on isn't the right road. Kesipta, Gary Gell, go this way. So if I let those exceptions go into action, oh, there's an arithmetic overflow, go to the operating system. Oh, there's a page fault, go to the operating system. And in fact, I wasn't even supposed to be on that road at all. I speculated, but my speculation was wrong. Then what should I do about the exceptions? Not do them, right? Cancel them or don't allow them. So we get into trickiness about what to do with exceptions as well. Okay, so we've got to basically buffer the exceptions or ignore them, hold them somehow until it's clear that they really should be occurring. Otherwise, we do wrong exceptions. Life gets interesting. Life gets interesting when you pipeline. All right, let's go into the details of the static multi-issue, the VLIW, very long instruction word. That's the one with multiple instructions in the same word. Basically, the compiler decides statically which instructions to issue and execute simultaneously. And the compiler puts them in. If they're in the long word, it means they will be issued simultaneously. That means it's the compiler that's giving the guarantee. These guys are independent from each other. No problem, they can launch and run parallel simultaneously. The compiler is doing the analysis to see, is anybody got data dependencies? Is anybody got control dependencies? If no, it doesn't put them in. If no dependencies, it puts them in. If yes, it doesn't put them in. So the compiler decides to pack 1 or 2 or 3 or 4 or whatever the capacity of the word is. The compiler decides how many of those slots can be filled. Okay? So this is called an issue packet. This is the set of instructions that are bundled together in a group. You guys can run together. We've got hardware for you, and you don't have any dependencies that are cause troubles. You can run together, okay, in a single clock cycle. Think of it as one large instruction. That's why they call this very long instruction word. Okay, the mix is usually restricted, a single instruction with several predefined fields. The compiler does static branch prediction and code scheduling. Remember what code scheduling is? That's rearranging the order of the code so as to reduce the control hazards or eliminate possibly the data hazards. Here was a good example over here. If I move this load up to here, I get rid of a data hazard, okay? If I can switch the order. But of course, to do that, I am speculating that these will be different. Now, if you remember, those look something like this. 4 on T0, 0 on T1. Now, they may be, in fact, different, but they may be the same. It depends on the values of T0 and T1. I don't know what they are, and neither does the compiler, my friends. And actually, the hardware doesn't know it either unless it goes and fetches and looks and adds 4 to one of them and adds 0 to the other one and then says, are they equal? Nobody will know until it's time. So that kind of analysis has to just be guessed. It would be foolish to try to do that in hardware or in software. Can't be done in software. Okay, now VLIWs, therefore, in order to do this, have multiple function units, multi-ported register files. What's a port on a register file? It's a place you can write into it or a place you can read out from it. Our current register file in the single pipelined MIPS has got how many read ports? How many read ports? 2. It can get an A bus and a B bus output at the same time. How many write ports? Only 1. It can only put in 1 value. Imagine instead a register file or a memory that had 16 read ports and 4 write ports. Okay, sure, can be. I can read 16 things in parallel. Can I write 4 things in parallel? Can I write 4 things in parallel? Yes, if they're 4 different things, but I can't write to register 1, to register 1, to register 1, to register 1, 4 different values at the same time, can I? So if I get same destination, I'll have to schedule it. But if they're different destinations, I could write in parallel. I certainly can read in parallel, no problem. And as many as you like. Just don't forget that for every port, you got a Kojimon multiplexer, which is choosing, and all the inputs come to that multiplexer, and then the control bits say which one comes out the port. So the more ports you add, the more Kojamon multiplexers you're adding. Yeah, so ports aren't free, but if you want to have multi-ported memory or multi-ported register files, you can do that. That's not hard. This is just a piece of hardware. But controlling it when you're doing multiple writes requires some synchronization. Okay? Are we clear about that? You got the idea? You want me to draw a multi-ported register file, or can you imagine it in your mind? We've already got one. It's got 2 read ports. We can get an A bus and a B bus data out at the same time. How do you do that? Give them 2 addresses, which go to the 2 multiplexers, which say, for this top multiplexer, send out that one. For this bottom multiplexer, send out that one. If you want, can you read the same thing out, both the A and the B? If you want, can you read the same thing out, both the A and the B? Sure you can. What if I had an instruction that said, multiply some value by 2? It might be very advantageous to forget the multiply, which is slow, and do this. What have I done? Take the current value, add it to itself, and stick it back. I multiplied it by 2. Does everybody see here that T0 and T0 need to come out the A bus and the B bus at the same time and go into my ALU. So here I want T0's value, here I want T0's value. I'm going to add it and stick it back, and over here I'm going to put it into T0. So the 3 addresses for, I forget what they're called. What is it? Remember? W and, anyways, whatever. You know, the write register and the A and the B, reading A, reading B. These are 5-bit buses here. I'm just going to give the value, register 8, register 8, register 8. That'll get me T0, T0, and T0. Okay? Yeah, you just give 8, 8, 8, and that means you'll pull out 2 T0s and you'll stick back the result in T0. Okay, so now, if you can do that, because there's a Kojamon multiplexer here, which is getting 8, and it's got all 32 registers, says that's the one you chose, and a similar Kojamon multiplexer here, which is getting all 32 registers, and says that's the one you chose. Why couldn't I have more? Why couldn't I have 16 ports or 32 ports or 8 ports or 4 ports? I could. And how about over here? Couldn't I also have more write ports? Sure. That's no problem. So we can have multi-ported register files. I just want to quickly convince you that that's not a big deal to do at all in hardware. Simple stuff. Just you got to know what a multiplexer is, bring the right inputs, give it control, bingo, your output is out. And then we're going to need a wider program bus, because obviously this thing has got multiple instructions. All right, we've come a long way now. I'm trying to really expand your mind with modern performance tools. This course is now moving into the advanced stuff. We're going to hit performance again when we go to memory systems and look at caching. Is everybody on board so far? I haven't lost anybody in the ocean or fallen into the waves or blown off the deck, have you? It's getting a little windy on this ship, a little bit of rough water that we're sailing through, but I think all of us can manage to hold on firm to the rails. You're not going to jump ship now, are you? It's a long way back to shore. It's too far to swim. We don't have enough life preservers anyway, so you're going to drown. So don't jump off the ship. Stay with the ship. All right, we're moving ahead. I can see the other side. I can see the shore. Maybe you can't. Oh, I don't see it, Hoja. We're going to get there. Don't worry. I'm the captain. I've been leading this ship for quite a few years. We'll get you there. Any questions about this so far? Any questions so far about the architectural choices? Now, I haven't gone yet into the superscalar. We're still talking VLIW. The dynamically multiple issue will be next. Just want to see if we're okay here. All right, so let's imagine that for MIPS, if we make a VLIW, that I have a 32-bit instruction word and another 32-bit instruction word, and I make the first one always an ALU operation or a branch, and I make the second one always a memory operation, load or store. So if it's a memory, it goes here. If I have 2 memories, I can't do them both at once. If I have 2 ALUs, I cannot do them both at once. But if I can find an ALU and a memory operation, or a branch and a memory operation, I can put them boom, boom. Right? So potential parallelism of 2. But as you know, if you look down a whole lot of instructions, you're probably not going to find an equal number of these with these. Probably not. Anybody remember a rough number? How often do we go to memory for load or store? 40%, yeah. So it's not going to balance out perfectly. And how many branches do I have on average? 20%, 15%. How many ALUs do I have on average? 45, even 50, yeah, numbers like that. In the simple examples where you've been doing CPI, I've been rounding things. But if you go look at the statistics in the back of chapter 3, I think it is, where it shows how programs run on MIPS, you can find out exactly how often instructions are executed. Okay, so instructions are always fetched, decoded, and issued in pairs. That would be the idea here behind our VLIW. If one instruction of the pair cannot be used, then we just put a no up there and leave it blank. So every time we fetch, we'll either be getting one or the other one or both, okay? One or the other one or both. And the other will be a no op. Therefore, in order to get 2 registers for this one and 2 registers for this one at the same time, I'm going to need to have a 4 read port and 2 write port register file, right? Because I could create a register result here, and I could create one here if it's a load. Load says put something in register. So I'm going to need 2 write ports and 4 read ports. Good thing we talked about how to do that over here just a minute ago, okay? And I'm going to need a separate memory address register because I'm going to have to create and hold a memory address. So look what we've done here. We've got a register file which is greatly changed, as you can see. I'm sending the ALU and the branch ones to my normal the R type and the branch ones to my normal ALU. But you notice that I also need to parallelize that. Do I need a full ALU to compute memory addresses? No, just an adder. Because a memory address is always the sum of two things? The offset and the register base value. You add them together. So I need to pull out a register value, which you can see, and need to get the offset, which you can see, and that creates the address. What's this? What's that? Why would a register value go straight to data memory? For store word, exactly. For store word, I create an address and I give a value, boom, I'm finished. For load word, I create the address and then I get the value and I bring it back. And over here, of course, I got to have 2 write ports. See it? 2 different addresses and 2 different places for the data. Got it? We've expanded our write ports to 2 and our read ports to 4. And a few other little things here. Okay? Not too much serious change to my data path, except that when I fetch here, look what I'm getting. I'm getting 2 at once. I'm getting a 64-bit word. Boom, it goes into here, right? And then I decode it in my control to figure out what to do, and I tell all these things what to do. So the control unit is going to be more complicated too. Anyway, notice that I don't have any hazard hardware. If I don't have any hazard hardware, that means that I don't have any load use allowed. Load and use cannot be together, and they can't even be in sequential instructions, can they? Because load followed by use is a problem. Load at the same time of use is a problem. Load followed by use it is a problem. So that means who's going to fix that? Since I don't have a hardware fix to stall, who's going to be doing the fixing? Compiler. Compiler's going to say, if you are load, using it can't be here, using it can't be here, it can be here. Right? So software is going to prevent load use hazards instead of the hardware. We won't need to stall because the software, the compiler, is sort of stalling for us by making sure it comes in the 3rd instruction, not the 2nd instruction. Okay? Now, the other thing that we want to mention is that's not the only kind of scheduling that it does. There's lots of scheduling that has to be done. Let's look at this little loop. We go back to loop here. We load T0. We use it right away. We store T0. We add and get an S1, and then we branch on S1. Can everybody see there's all kind of dependencies here? That's one, that's one, that's one. Got it? See the dependencies? If I don't have it fully back in T0, I'm going to have forwarding hardware to use it here, but it's that load use, so that's a problem. And then here, what I'm trying to do is store it. No, I'm sorry. Here I'm creating a value here, and then I'm supposed to be sending it into memory here. Is that too soon? Okay, that issue. And then finally here, I create a value, and then I'm supposed to use it and test on it before it's even back in register file. Now, what am I going to do? When I schedule as the compiler for this VLIW, I have to choose instructions that are going to avoid pipeline stalls. And the instructions, or since we don't have stall thing here. We avoid problems, let's say it that way. So instructions in one bundle must be independent from each other, and I must separate load use instructions from their loads by one cycle. And I must notice that the first two instructions have a load use problem. I already did that. And the next two and the last two have got data dependencies there and there. And I should assume that branches are always perfectly predicted by the branch prediction hardware, or I will. And so that leads me to the following set of scheduling. Okay? If this is not in, if I don't think about the loop part, if I just think about the dependency part, then what we're going to have to do here, as you can see here, is put the T0 creating load here and not use it here but here. Everybody see that? So that's my first one that I fixed. I scheduled it there. The second one was, go back and have a look. Second one was T0 being changed in the add unsigned and then written into memory in the store word instruction. Okay, so now we've got it being changed here and being written here in the next one. Is that okay? It is if we can forward our data. Remember, we can pick it off here. It's an add, so it's the ALU. It means we can get it right off the mouth of the ALU. We don't have to wait till it gets back into the register file. So yeah, that normal forwarding will get me that to here. And then the third one was creating S1 and in the next instruction using it. Okay, is that okay to do? Create it and then use it in a branch? The next instruction? The answer is no, it isn't. That's going to cause a stall, if you remember. We looked at it before. But here, I don't use it in the next instruction. I use it in 2 instructions later, so I avoid the stall. I still have to forward it. Where do I forward it to? Where do I forward it to? Remember, I'm going to forward it using the forwarding hardware. Where's it going to be forwarded to? The new multiplexers that I put just before the comparator, remember the extra comparator in the decode stage. All right, so I'm going to forward it right into there. Okay, great. So I've now scheduled it, and everybody can see the data dependencies are taken care of. And 5 instructions ended up getting packed into 4 very long instructions. So it's not very good, actually. Okay, 5 went to 4. We got a little bit of speed, and we added hardware where you can see no parallelism, no parallelism, no parallelism, finally some parallelism. So did we gain anything much from this? Not much. But we haven't unrolled the loop. Don't forget, this thing is in a loop. That means that what I really want to do, if you would allow me to, what I really want to do is do this, 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 then do this, 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 then do this, 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 many, many times. So actually, I'm going to have many executions of this, but with different values of S1. And I'm going to have many executions of this, and many executions of this, but with the new values of S1, and many executions of this. Well, when S1 changes, that's a totally different memory location, creating a totally new value, which creates a totally new value. It's independent. So the first iteration through the loop, and the second and the third and the fourth iterations from the loop have nothing in common data-wise. All they have in common is what? The place in memory that they're operating on. They move slowly through memory. Can everybody see that? The data is completely different. All we're doing is moving through different locations in memory and doing the same thing. That's what this loop does here. Okay? It's an array. T0 is an element in an array. The base of the array is S1. So I add a scalar to the value I got, and the scalar's in S2, and I put it into T0, and then I store it back into the array. So I took something out of the array, worked on it, and put it back. Everybody see that? Then I decrement the pointer, and if I'm not done, go back and do it again. Take the next one out, do something to it, and put it back. Decrement the pointer. If I'm not done, go, got it? It's just moving through the elements of an array, doing the same thing, but on a different location each time. Datas are completely independent. The locations are just sequentially moving. You can see here that I'm changing S1 by 4 each time. Okay, so now imagine that you could do it in parallel. What would it take? Hardware to go get it, add the constant, stick it back. If you had a whole bunch of those, just like we talked about earlier, you go get in parallel, add the constant in parallel, stick it back in parallel, if you could. All right? We're not going to do that because we don't have that many independent memories to be able to fetch independently and write independently. What we're going to do is we're going to pipeline it, and we're going to say that some of my going and getting can overlap with some of your putting it back, and some of my putting it back can overlap with your going and getting it, because we're working on different places in memory. You got the idea? Yeah, that's called unrolling the loop. A loop means do the same things over and over. If you unroll it, let me see if I can say this straight here. That loop does 3 things essentially. Go get it, change it, put it back. 4 things, and then change the loop. The last 2 are just loop control. I don't know if you can tell here, but this one changes S1 and I find out if I'm done or not. Okay? So these are loop control. Here's the actual activity. Okay? If I were to unroll this loop, instead of a tight little loop with 3 activity instructions and 2 control instructions, and doing that 12 times, can you imagine a loop that has 36 activity instructions and only executes once? Well, it doesn't even need to be a loop. If I just do those 36 instructions, I'm done. Or how about a loop that has 18 activity instructions and I do it twice? 2 control instructions and 18 activity instructions, and I just do it once and go back and I do it again and I'm done. I've done everybody. Or how about a loop that has 12 activity instructions and 2 control instructions, and I run it 3 times? Or how about a loop that has 9 activity instructions and I do it 4 times? Or how about, got it? Got the idea? Yeah, that's called unrolling the loop. So you take little tight loops and you make them bigger, so you execute them less times, but you still get the same amount of work done because you iterate the code you're doing in the loop slightly different to make sure, okay, got the idea? That's called unrolling a loop. Now, why would that help us? Why would unrolling a loop to have more activity instructions help us? Yeah, because then I could schedule them better to fill in some of these blanks. Then I could schedule them better and have a higher degree of parallel. As long as I can find 2 that are independent from each other from different places in my loop. And obviously, if I have a loop with 36 activity instructions, I got a lot of choices. They're all independent. They're working at different locations, 12 different locations in the memory. Okay, do we got the idea behind that? Let's take a break, and I'll unroll the loop, and we'll come back to that concept after break. Take 10 minutes.